problems in homework 2. So first comment on this is that first two problems are most important. If you will be able, if you are confident with problem number 1 and problem number 2, you are pretty much pass. So this is enough to have a pass for this model. Because what I want to say, so you will have 5 problems in the exam paper. One problem will be something from this homework, which you're supposed to submit next week. Then every second week there will be more submissions. Then you will have 5 marked homeworks. So I don't count the one which was last week. Yeah. So 5 homeworks prepare you for 5 problems in the exam paper. This homework now, this first marked homework, prepares you for first problem in your exam paper. And this now, getting back to these problems number 1 and 2. Problems now 1 and 2 are about finding, well, in fact, it's problem 1, most important one, is about finding fixed points or equilibria or stationary solutions and to analyze their stability. And this kind of problems appears at least 3 times in your exam problems. It will be an exam in problem number 1, in problem number 3, 4, and 5. So you will see this problem of finding, so for these 4 maps, it's called fixed points. For flows, it will be find stationary points or equilibrium. But it is the same problem, finding fixed point and analyzing its stability. This problem will be met 3 or maybe 4 times in your exam. So if you are comfortable with this, you will definitely pass this model. Now, well, so here there are some technicalities, some difficulties, which you may or may not see on your exam. Now I will go to tablet mode. So what is main idea in here? Main idea in here is that you have a function f of x, which generates this function f of x, which generates your map. And so you're supposed to find fixed points. So you have these maps, map x plus 1 equals to f of xn. F is this. You just replace x by xn. And fixed points are roots of x equal to f of x. So you try to understand why it is, because for fixed points, it is points where xn equals to xn minus 1, and so on up to equals to x naught. And so if this was, well, let's put it like this, xn plus 1. So this is xn plus 1, and this is xn, and this eventually you get this x equals to f of x. So you find, so you now, I'm not going to show you how to solve this. So you solve this equation. Your f of x is quadratic. F of x quadratic. And therefore, you can have up to 2 solutions. Up to 2 roots, which are fixed points. And now, so peculiarity of this problem is that you have 2 roots. You should check that your roots in this domain for this value of parameters, because your x, let's say x1 is depend on mu, x2 is some function of mu. So you will check whether x1 and or x2 are in this domain -1, 1, when mu is between 0 and 2. So it's technical problem. So you're supposed to do this. So this is one part of story, and second part of story is about stability. For stability, so this was theory, yeah. So this is piece of theory which you use here, and for stability you use another piece. So for stability, what you check derivative of f, and so if you found, eventually you'll find which of these fixed points are you're supposed to consider. And then for this fixed point, for this, so when df over dx when x at fixed point should be by absolute value less than 1. So it should be, or you can put it like this, df over dx at x capital should be between -1 and 1. So you find where under for what values of mu this. From here you find values of mu when x capital is stable. I did it for logistic map on the lecture, so you can look this again. Sorry. So you can look at this. I don't remember what lecture it was. At least it was in lecture 4. Maybe it was somewhere else more. Just so this is about stability analysis. You find derivative of your function. Yeah. So I can tell you. So in this problem, you will have 2 fixed points, but only one of them will be in this domain between -1 and 1 for given values of mu, and therefore you will need to do it only once. Questions? Do you have any questions? Anyone?
Yeah, sorry, when on the first slide when you had f of x is equal to x.
Yeah, this
can you explain that bit again?
Okay. So this so for fixed point again, at fixed point, definition of fixed point by definition. Xn, say +1 equals to xn. So, and then what we want to know, we want to find what should be value of, well, I can put it like this, even x1 equals to x0. So what values of x0 I should find? You see, x0 is any number between -1 and 1. And fixed point, it's this kind of values, particular values, for which this is satisfied, x1 equals to x0. And then we say, okay, assume this is x, fixed point is x, and then x1 should be equal to x, and x0 should be equal to x, and therefore x equals to f of x. Yeah, so in this here, well, I can put it like this, x equals to 1 minus mu x squared. Roots of this are your fixed points. So it is quadratic, you will have 2 roots, but then you will need to check whether your roots are between -1 and 1, when mu is varied between 0 and 2. Is it okay?
Yeah, that's cool, thank you.
Okay, more questions? Okay, as I say, this is very important problem, because this problem, we will talk a lot about fixed points and stability. This is one of main themes here in this model. Okay. So problem number 2. It is about two periodic solutions. Consider further the map, so it's the same map as in problem number 1. And we want to investigate properties of second composite. And this, so it says shows that f2 of x has two fixed points. What it means? It means that, well, there are two ways to look at it. At one, if we look at xn plus 1 equal to f of xn, then from here we can say that xn plus 2 equals to f of xn. F2 of xn. So I hope you understand this, because xn plus 2, well, I will write it. Xn plus 2 is f of xn plus 1, but xn plus 1 in turn is f of xn. And then we have this two composite map, f2 of xn. So, and now, so what we have, so if we have two periodic solution, for two periodic solution, xn plus 2 should be equal to xn. And from here we get that two periodic solutions are roots of equation x equals to f2 of x. Does it make sense? Any questions here? So this is, if we want to find, so roughly speaking, if we want to find two periodic solutions, we need to find fixed points of this map. But there is a small complication here, because, well, maybe it's even not complication, it's just some property of this. So f2 of x, if f of x is quadratic, this will be a fourth order, yeah, polynomial, fourth order polynomial. And therefore x equal to f2 of x will have 4 roots, up to 4 roots. But then the peculiarity here is that roots of x equal to f of x, also roots of x equals to f2 of x, because fixed points of this map also satisfy this condition. If xn plus 1 equals to xn, then xn plus 2 equals to xn plus 1, and therefore xn plus 2 also equals to xn. Therefore, two roots of this, also roots of this. And so two roots of, but we have here two extra roots. And these two extra roots are proper to periodic solutions. So there are two roots which are just fixed points. Eventually they satisfy condition for two periodic solutions, this condition. But in addition to fixed points of our original map, we will have two extra roots. And these two extra roots will give you two periodic solution. Did it make sense? Any question here? Is it okay? Okay. Then what we need to find, so again, we find fixed points. So this statement here shows that it has two fixed points. It is a bit different. So it's like we are looking for, we can consider like map like this. U n plus 1 equals to f2 of u. We can put this, we can consider this kind of map. Yeah, so instead of function f, now we use two composite. And then we can treat these roots, we can treat roots of this equation as fixed points for this. solutions of this map, well, of previous map. Now we don't have here two composites. So fixed points, again, fixed points of this are two periodic solutions for fixed points of this are two periodic solutions of this. Did it make sense? Okay, then what you need now to do is to find fixed points of this. So the fixed points of this are roots of this x equal to f2 of x. And what you need, you just need to put this is f of x. f of x was, what it was, 1 minus mu x squared, yeah? So f of 1 minus mu x squared will be 1 minus mu. Instead of x, you put again 1 minus x squared, 1 minus x squared. So this is your equation. You will need to find roots of this equation. Now you see there will be 4 roots, but 2 roots you already know. 2 roots was roots of this. X equal to mu 1 minus x squared. And therefore you can find 2 other roots of this.
Is it not meant to be in the brackets 1 minus mu x squared?
Ah, yeah, yeah, I forgot. Thank you.
Yeah.
Yeah, correct. Thanks. It is good. So if you see anything, any mistake, stop me and correct me. Okay. Questions? So this problem, it appears. Eventually, you will need to find two periodic solutions on your exam. It will happen once, most likely in problem number 1. And this is quite time consuming. Solving this equation, dealing with this equation is time consuming. Look how I was doing this. It was lecture number 5, I think. Lecture number 5. Look again how I did it for logistic map. And well, you practice it now here. And if you do it well, if you do it like 2-3 times, it should be fine. And you will be ready for exam, at least for this problem in exam. Okay. Questions? Problem number 3. So this, for some reason, well, it is not so easy to understand what is this. But this is what you will use, or what you used already in problem number 2. So let's put it like this. This problem, and I think all others, 3, 4, 5, 6, remaining 6 problems, or 4 problems, they are pretty much specific. They are not common problems. But on the other hand, it's good if you practice on these specific problems, you will understand better all material. So this, you already had this, was in problem 2, but n was equal to 2. So it's generally, so I think I gave explanation for this in one of my lectures. I can try to do it once again. So what we have here, assume we have y as a function of u, and I assume we have u as a function of x. So from here we can say y is a function of x, so f of x, or to composite f of x. So this is fine, we understand it. And then dy over dx would be df of u over du times df of x over dx. Is it okay? Should be okay, yeah? So it is this here and this here. It is chain rule. Now, if I want to find dy over dx when x has specific value, say x naught, then it will be df over du when u equals to f of x naught times df over dx at x naught. Yeah. And now what I want to do, I want to now get to these notations here. To get to these notations, I will put it here. To get to these notations, I replace y by x2, u x1, and x naught. And then if we put it like this and put it here, it will be dx2 over dx naught, this one. This one will be dx2 over dx1, and this one will be, I don't have space here, dx1 over dx naught. So this eventually transfers into what we want after this change of notations. Was it okay? So this, I did it for n equal to 2, but you can probably see that it could be done for any n, not necessarily 2. Was it convincing? Questions? Okay. Now second part of this problem. So here it is quite specific. Well, this one, it is good if you do this and think about this, about first part of problem number 3, you will feel better. You will see. So it's not like following procedure, it's understanding procedure. So this is for understanding procedures. And here it's again, so it's also, now we will use what we learned in first part of this problem to answer this specific question about superstable n cycle. So first of all, what means superstable n cycle? Superstable n cycle means let's assume we have n cycle, and in this n cycle we have x changing, like, let's say, well, I used x capitals usually, x capital 1, x capital 2, and so on, x capital n. So we have n values of x, and n cycle would mean x2 is equal to f of x1, x3 equals to f of x2, so on, xn equals to f of xn minus 1, and most important part here, x naught, x1 equals to of f of xn. Then you see now it will be cycle. So if we had assumed we started with x1, the next 2 will be function of x1. So next point in our solution. So in our solution, if we started with x1, so this was equal to x naught, let's say. X naught equals, so our original value of x was equal to x1. Then in our solution, x1 will be equal to x capital 2, and so on. Xn minus 1 will be equal to x capital n. And then next will be x naught again. So it will, so these values will keep repeating again and again. Yeah, it makes sense. Maybe I was a bit messy in my explanation, but hopefully you understand at least this story. This story here explains what is n cycle. It's like, so if n is 2, it will be 2 cycle, 2 periodic solution, and with 2 periodic solution, it was more or less explained, it more or less easy to understand. Now, superstable would mean that dxn over dx naught equal to 0. So it is was definition of superstability. So or dfn, it is what is sensitive over dx at say at x1, for example, is 0. But if it's 0 at x1, it also will be 0 at x2 and so on, because it is the same cycle. Or we can put it like this: dfn over dx at x equal to x1 equals to df over dx at xn times df over dx at xn minus 1, and so on. Do you understand why it is? So this is what we get. This is basically this, and it was shown here. And what it means now, if this is 0, if this derivative is 0, if this derivative is 0, it means that so this derivative dfn, this let me use. Okay. This derivative is 0. And this derivative is product of these n derivatives, then it will be 0 if at least one of these guys is 0. Yeah. So this means that f df over dx is at x1 0 or at x2 0 or x3, or so at least for one of these x's is 0. And this means that one of these x's, so df, so next point, what we remember, so this was about logistic map. What we know about logistic map, df over dx is 0, mean only in one point when x equals to half. So only here it is derivative is 0. It is stationary point for this x times 1 minus x. xn minus 1 xn. Yeah, is it okay? So therefore, either x1 or x2, well, x1 capital or x2 capital or xn capital, one of them should be equal to is half. So since we don't care how we call them, we can say let x1 is half. And if x1 is half, we know that f of xn is also half, but because it's equals to x1. And this in fact is fn of x1. So this means that this is half and this is half. Therefore, we get half equals to fn of half. And this is exactly what we're talking here about. This. And now we just need to apply this for n equal to 1 and n equal to 2. If n equal to 1, well, maybe, well, I don't know. Do you understand how to proceed? So I don't want to show you solutions. I want to explain how you're supposed to do this. It is indeed difficult quite often. You don't know how to start. So I'm giving you ideas how to start, but maybe the rest you will do yourself. Is it okay? Questions? Okay, tell me, was it useful what I'm talking about? Did it explain anything?
Yeah.
Okay, good. Then Do you have any questions? Well, let's put it like this. I don't know. If I ask if anyone doesn't know how to proceed, no one will answer because it's not a good question. Okay, so if you hesitate to ask me now, you can email me and we can discuss it. We can discuss it. By the way, it's a good point. So this homework is due on next Tuesday, and next Tuesday I will have. I decided to keep my office hours on Tuesday because it will be your last chance to ask me something before you submit your homeworks. So we can meet. You can email me, or you can try and wait. If something's still unclear, you can ask me. You can come to the same Zoom room on Tuesday. I think it was 1 to 3, from 1 hour to 3 hours, from 1 o'clock to 3 o'clock, and ask me. Okay, and I will go to problem number 4. This problem, in fact, was addressed when I was talking about superstability. I don't remember what lecture number it was. So one of lectures was devoted to it.
What time on Tuesday is your office hour?
From 1 o'clock to 3 o'clock.
Okay.
So it is, I think it was announced at some place. It was in introduction PDF, and maybe it was in the first announcement. I decided not to change it, not to mess with this. It's hard to. Maybe it would be, you see, this online session changed, and it didn't change the way I would prefer. I would prefer, for example, to have 1 hour one day and 1 hour some other day, but they decided to keep 2 hours in one slot. And maybe I should also then consider splitting my office hours in 2 different days. I don't know, but it's okay. So I will have 2 hours on Tuesday, but if you want to meet any other day, just email me, we can arrange a meeting. Okay? So problem number 4, it is about period doubling cascade. So what we have, this is when I was explaining it, I was plotting something like this. So this was orbit diagram, it's called. So this is, I will keep this xn. No, it's not xn. So it's orbit diagram. This is our parameter mu. And this is our fixed points x. So this was fixed point x2. Then these two guys, then it become unstable, and there were this x3 at x4, or its 2 periodic solution. x3, x4. Then they were becoming unstable, and we were getting more. And I was considering this. Now, when we get 2 periodic solution is 2 to the power of 1, and therefore we will call it, this one is mu1. Here, 4 periodic solutions, 4 is 2 squared, we will call it mu2, for example, and so on. This will be mu3, and so on. So it is the way I presented in my lecture, but here it's a bit slightly different presentation. Well, it is should not make any difference. Again, mu, this is x, so this is our x2, this is our x3, x4, so this is our others. So what they say that mu equal to 2. So this x2 is super stable, and therefore we will call it mu naught. Somewhere here, when it's super stable, we will call it mu1. somewhere here where it's still super stable, we will call it mu2. It's slightly different definitions of mu1, mu2, mu3. Sorry, here should be mu3. So mu n is here is place. Where 2 to the power of n solution occurs. And it is here. And here, mu n is place when 2 to the power of n solution is super stable. Slightly different definitions, but everything else, so all conclusions are the same. So there is still Feigenbaum constant delta. So we can formulate it in terms of these mu's or in terms of these mu's. The answer will be the same. And so what is here? So here we have this, what you can, so this is, I called it mu2. It is up to you how to call it. This is mu3. This is mu4. Mu4 means 2 to the power of 4. N equals to 2 to the power of 4. Yeah? Does it make sense? So this is n and so on. So here we can have for n equal to 2, by the way, I found this mu in one of these lectures. Mu, I don't remember what it was, equal to 1 plus square root of 5. Yeah, am I right? I don't remember. Let me check. Yeah, 1 plus square root of 5. This is mu1. And mu0 we also found mu0 was equal to 2. Therefore, you have mu's from 0 to 5. Mu5. Oh no, this n equal to 66 is mu6. This is 6. This is 5. Am I right? 2, 3, 4, 5, 6. Yeah. And now what you need, you just need to check using definition of mu. Mu equals to, no, sorry, not mu. Delta, first Feigenbaum constant, is mu n minus mu n minus 1 over mu n plus 1 minus mu n. So this was how you find delta, and this delta, let's say this delta n. Then these deltas, they converge to constant, which is called first Feigenbaum constant. Converges to delta when n tends to infinity. And so what your task here is to find values of delta. Just find delta 1, which is mu1 minus mu0 over mu2 minus mu1. Then find delta 2, also use similar formula. And you can find up to, I don't remember, delta 5, I think. For delta 5, you have for everything. For delta 6, you don't have. So then you can see that these deltas are pretty much close to each other, and they like eventually converge into something. Then you can take this value of delta 5, which you found using these numbers. These three numbers you will need to find delta 5. And then you just follow this procedure which I have shown in this corresponding lecture, where I was find mu infinity, place where 2 to the power of infinity solution is super stable. So here sounds like this in terms of, so in terms of this superstability, it's like this, but then this distance between place where it becomes super stable and place where it appears, it is probably 0. So you can consider it as 0. So it is, so here, chaos. So that's how you get chaos. Questions? Any question? So there is no feedback to what I'm talking about. It's difficult. So of course, I would prefer to believe that everyone understands what I'm saying, but most likely it's not true. Well, there are two parts. First is my ability to explain, and it's possible that here, I don't know. So if you have any question about this is, I mean, it's quite conceptual problem. So again, as I said, problems number 1 and 2 are more technical. You're supposed to professionally do problems number 1 and 2. Problems 3 and 4, they are not standard problems. But when you do them, you understand better what is going on in these one-dimensional maps. Okay, so I'm going to the next problem. Problem number 5. I think this is the easiest problem. It was also in one of my lectures about quadratic maps. I think it was last one. Quadratic maps. I think it was last one on week 2. On week 3. So it is lecture number 9. So everything is in here. So so this is like problems number 1 and 2, just to follow correct procedure. So the idea here, general idea about quadratic maps to be isomorphic, is that, let's put it like this. So we have this quadratic map, for example, logistic map. And for the logistic map, we have this orbits diagram. n plus 1 equals r n 1 minus un. So this will be this r, no. So we have all of this. And this is, for example, R1, this is R2, and so on. And now assume we have this map. Xn plus 1 equals to 1 minus mu xn squared. So for this map, by the way, I didn't plot it, yeah? So this is, let's put it like this. So it was defined between -1 and 1. And it is something like this. So this value is 1 minus mu. So if mu is less than 1, you will have this kind of shape. If mu is more than 1, it will be something like this, sharper. And if mu is equal to 1, it will be this. But anyway, so this guy also has something like this. I'm afraid to plot it. I don't remember how it looks like. This orbits diagram. If I find it somewhere. I had orbit diagram for this map. So when mu is increasing, okay, it should be something like this. Mu, this is x, and it would be something similar. I think it should be, I think mu is, I am afraid. So here something, I'm afraid to plot here something not correct, something similar to this guy. But what we can say R1 is value of your parameter R here when you get to periodic solution. And you can find values of mu1 and mu2 values. You can find from R1 and R2. You can find mu1 and mu2 if you know R1 and R2, but you will do this, you will be able to do this if you complete this problem number 5. If you find this transformation, which transforms this map into this map. No, it's this map, sorry, to this map. Okay, I will show yn plus 1 equals to a yn 1 minus yn. Now here you replace yn plus 1 as a way around. Sorry, let's put it as a way around. Because we have function x as a function of y. Let's say xn plus 1 equals 1 minus mu xn squared. Now, instead of xn plus 1 here, we will put a yn plus 1 plus b, yeah, because that's what we use. And this should be equal to 1 minus mu times, and here instead of xn, we put again a yn plus b squared. And next part, yn plus 1 is a yn 1 minus yn, because you use it here. You use this to replace yn plus 1. And therefore, you will have a kind of equation, but in this equation, you should equal, so there will be like something times yn squared here, plus something times yn, plus something doesn't depend on y on the left hand side, and here you will have same plus also something, and you will have 3 equations. You should this equals to this should be equal to this, and this should be equal to this. So you will have 3 equations, and these 3 equations will give you what should be a and b first, and then they will give this correspondence. So this is general, so I don't want to do it, otherwise it's pointless to have this as a homework, but I told you how to do this and almost everything. Questions? Watch again this video about quadratic maps. What I did now, I just repeated what was done there. I did there for slightly different this function. This function I think was different there, but it was also, so I was transferring to logistic map. Questions? Problem number 6. So problem number 6, I will be talking about this next my video. The first video for week 4 will be devoted for these solutions, for intermittency. It's very interesting solutions. Well, I can tell a little bit here. What is it? Okay, so we discussed periodic solutions, like 2 periodic solutions. We know what is two periodic solutions. We know four periodic solutions. We know even where they appear. Two periodic appears at 3, and so it appears at 3, yeah, and becomes unstable at 1 plus square root of 5 and whatever. So this two periodic for, let's put it, so we have un plus 1 equals to r un 1 minus un. For these periodics, r equals to 3 when the periodic appears. So this appears at r equal to 1 plus square root of 5. I didn't show this, but you can guess from what I was talking about period doubling cascade, because in period doubling cascade, when two periodic solution becomes unstable, we have four periodic solutions, and we know where it's so it's stable from 3 to 1 plus square root of 5. Therefore, at this value, four periodic solutions occur. Yeah. So, and we can find 8 periodic and so on. But the question is, what is about 3 periodic or 5 periodic? How to find them? And it is same procedure as before. So this illustration for 3 periodic, maybe I will put it here before I will go to this illustration. So for 3 periodic, un plus 3 equals to un. 3 periodic. And these are fixed points of this map. Let's say un plus 3 equals to f3 of un. And therefore, these are roots of u equal to f3 of u. Roots of this give us 3 periodic solutions. And we can ask how many roots it has. So if f is quadratic, then two composite map of f would be fourth degree polynomial. So quadratic has 2 roots, fourth degree has 4 roots, and f3, I will put this here, f3 is of 8th degree. Yeah, does it make sense? Again, f sec 2 degree, it's quadratic. f2 4th degree, and f3 8th. Well, it's every next time, so it will be doubled. And this means that this will have up to 8 roots. So we are not going to these roots, but this illustration is how it goes. So this is f3 function. It is f3 function for logistic map. And what we have here, so now this f3 has indeed, at least for this value of parameter, 8 roots. This is first root, second, third, fourth, fifth, seventh, and here we have 2, 3, 4, 5. This is 6. Sorry. 6, and here 7 and 8. 8 roots. Now this guy is fixed point, and this guy is also fixed point. These two fixed points for f of x, they will be the same, because fixed points for f of x, they are also 3 periodic. They should be 3 periodic if xn plus 1 equals to xn. From here you conclude that xn plus 3 also equals to xn. And therefore roots of these also roots of these. And therefore these two roots are just fixed points from the original map. But we have here two extra sets. So we have 6 more roots, and these 6 roots make 2 extra sets. So this red one, red, red, and red. This is one 3-periodic solution. So for this solution, there will be jumping. If we started at this red point, next will be, I think, this, and the next will be this. Am I right? Yeah, so this, well, it is, we should see here it is fixed point. So they all fixed points here. But if we look at logistic map, if we start at this point, this red point, then next will be this, then next will be this, and then next will be, I think it will be this, and the next should be this here. This dark point, and this dark point. These three dark points, they shape another 3-periodic solution for logistic map. So it will be another 3-periodic solution for logistic map. But the difference between these two 3-periodic solutions is that one of them is stable and another is not. So they appear like this. One is stable, one is not. But this guy, which is stable, it will eventually become unstable if our parameter is further changing. If, for example, our parameter R in logistic map is further increasing. So what happens? Maybe I will show it. I will try to show it here. So if, for example, R is increasing, it will be this, so larger R. And if here derivative of our function, this function was between, so it was, let's say, negative, but it was shallow here, shallow. And here it is sharp. And when it's too sharp, we know it becomes unstable. So it is what now, how it happens. When we get 3-periodic solution, when it just appears, it is shallow here. It is, so it's increasing, our function is increasing here, but it increases faster than diagonal line, therefore its derivative here is more than 1. This guy is unstable. But this is stable. This guy is stable when it appears. But with increase of R, this derivative of our function point of intersection becomes, so our function becomes sharper, and derivative eventually will be less than -1. It will be too sharp. And then this will be also unstable. Yeah. So this is, it's, by the way, here, maybe I can tell you, I can talk about this kind of, I am just showing this piece, one small piece. So assume, so this is our function f. This is diagonal line. And so, okay, I will put it here, y, I say y equals to x. So now if we started somewhere here, now I am getting closer to to this problem number 6. Assume we started with x naught here. So next x1 will be this x1. Then x2 will be this value, so this is x1. Then it will be x2. So what the point here is that if this corridor here, if it gets narrow, then our solution can get stuck here for quite a long time. So in order to get through this place, it will take quite a lot of iterations. It's at one hand. So if f of x above diagonal line but very close. We get stuck for a while. And so this for this while it will look like fixed point, yeah, here. But then eventually eventually will change behavior. So change behavior when it gets out of this corridor, it will go somewhere else. And this is called intermittency. So my next video will be devoted to intermittency. But anyway, so if you listen it here, listen lecture, it will be just better probably. And now, so what happens here? Here we have, if our parameter r, for example, this is for logistic map. If parameter r is at this value, we have stable. So at this value of r, we will have this three red points. Stable. Stable. We have stable. Here we have stable 3-periodic solution. But if R is reduced, we are getting reduced, then we will not have, if it's reduced, then it will go like this. It will not touch here, it will not touch here, and it will not touch here, this diagonal line. And we will not have 3-periodic solutions. So 3-periodic solutions appear only when our function touches this f3 function, touches this diagonal line. If it's not touching, we don't have 3-periodic. But when it's very close to touching, we will have here this corridor, which I was talking here and here. This will be this kind of corridors. And therefore, we will see, like for some while, we will see 3-periodic solution, something like very, very close to 3-periodic, but then it disappears, and when it disappears, it is chaotic solution. So this will be bands of 3-periodic and with bands of chaotic mixed. And this is intermittency. Okay, and the next point, when we change parameter, it crosses this, and when it crosses diagonal line, we have, so I might be able to put it here, depending on parameter value, I will keep R. We have either no fixed points or 2. Back to here. This is no, but So if it crosses, now we have to here fixed point and here fixed point. So this is what it means. It means that we have a bifurcation. We have a bifurcation when F touches diagonal line. And this is last type of bifurcation. I was not talking about this as far as I remember. It's called fold bifurcation. I will derive all this, I will talk about all these bifurcations later on when I will talk about flows. Eventually, it's much easier to present theory on bifurcations on flows rather than on maps. But so on the other hand, with maps is easier to get to this chaotic dynamics. And it's why common practice is to start this course with maps. We get straight away to what is declared on the title of this model. And then later on, when I will be talking about flows, I will talk about these three bifurcations: fold, transcritical, and pitchfork. So this fold bifurcation, it's always when we have fold bifurcation one, when we have two fixed points, one is stable and another and second is unstable. It is a feature of fold bifurcation. When two fixed points appear, one of them is always stable, another is unstable. Like here, two appeared, unstable, unstable. Here two appeared, unstable, unstable. And here two appeared, unstable, unstable. So this is fold bifurcation. And now this story. Yeah, now we want to talk about these stories. I will show this story in more general way for logistic map, well, for any map maybe, on the following in the next lecture. The idea here, maybe I will show it again. So this is our function. This is diagonal line. Now what we want to do, so if f of x is close to diagonal line, somewhere here, and this value, so in this I will put like value of x naught. And let's say at this place we can put x, we can present f of x at this closest point as Taylor series or as linear approximation or quadratic approximation. F of x naught plus derivative of f at x naught times x minus x naught plus second derivative at x naught, this is half x minus x naught squared. So we can put it like this. It's quadratic approximation or second order approximation. Now, this guy is this value. So this value, so here, y equals to x is here. Y equals to x. So here it will be f of x will be equal to of x naught will be equal to x naught plus something very small, say epsilon. So it's this distance is epsilon. Epsilon is the distance. So this is first. So here we can put x naught plus epsilon. Now, at the point where this function f is close to a diagonal line, its derivative is equal to derivative of diagonal line. Derivative of diagonal line is 1. So here we put 1. And what is in here, we can just like half of, so we can use some notation, for example, a. So what we will have? We will have f of x, now quadratic approximation of this, is x naught plus epsilon plus x minus x naught plus a times x minus x naught squared. I don't remember what the next. X naught cancels. So what we have x plus epsilon plus a times x minus minus x naught, correct. It is correct. It's correct. Now, what for our map it will be like this: xn plus 1 equals to f of xn, and therefore it equals to xn plus epsilon plus a times xn minus x naught. And in our case, x naught is given. Now I understand. I was confused why we have this value. X naught is this 0.03. Oh, it was, yeah. So this is our equation. And now we can put it like this: xn plus 1 minus xn equals to epsilon plus a times xn minus 0.03 squared. And the only trick we want to have here is what we can say. We can say xn plus 1 minus xn divided by 1, which is xn plus 1 minus xn divided by n plus 1 minus n. So this trick, just to remember, it is not quite easy to understand. So this is, we can put it like delta x n, and this is like delta n. Change in time, roughly speaking, and this change in function. Therefore, we can put it, and then we can say, we can replace it by dx over dn. So this is a difficult trick. I'm supposed to tell you about this, but it's pretty much not very convincing. But this trick you're supposed to use in this problem. Dx over dn. You need to use this trick to find how x changes with n. Dx over dn now is x plus epsilon plus a times x minus 0.03 squared. And this is differential equation for x. You're supposed to solve it. So it is math 101 problem, generally. Good. So I will not solve it here. You will do it yourself. But I brought it to this point, at least. So this last problem caused me many difficulties. It's just because this is material of the next lecture which I didn't prepare yet. Questions? How many of you? So I will stop share screen.